I've got to remember, yeah, I'm bothering Andrew Wilson. I'd forgotten that as well.
Yeah, I think it'll be in the
I haven't read the thesis yet. That demonstrates that. That's recorded.
Gotcha.
It's all right. I'm editing the recordings, so I'm in charge at the end of the day. So I can edit anyone to say anything they like. Sorry, it's gone too long. Over to James, who's going to talk about. Is he all set to go? He's technically set. So yeah. So just to introduce James, if we want to do whole countries with Gaussian processes, we end up with big scalability problems, and that's been a real focus. And James noticed this really cool thing coming out of these inducing variable tricks about how you could actually take work by David Bly on stochastic variational inference and apply them to Gaussian processes, giving us the potential to do approximate inference for millions of data, and that's what he's going to be talking about.
Thanks, Neil. I should begin my talk with a small apology. My talk does contain quite some technical material, because I guess that's my sort of contribution to what's going on here. But I'm not going to apologise for putting technical material in, because that's what my talk's about, but I shall apologise for not apologising for having technical material. So the talk looks like this. I'm going to talk briefly about the motivation, which is very quick. Neil pretty much summed it up. I'm going to recap sparse Gaussian processes, which I talked about just the other day. I gave a sort of tutorial introduction to what was going on there. And in particular, I'm going to show this trick which introduces some factorization in a likelihood. I'm going to talk about how we can then use that to do stochastic variational inference in one of these things. And then I've got some moderately preliminary examples to show you afterwards as well. Okay, motivation. To do inference in a GP, then we have to invert the covariance matrix, which requires the order of n cubed operations on the CPU and requires n squared memory, order n squared memory as well. And when I say inference, I pretty much just talking about inverting the covariance matrix. So you probably have to do this many times. If you want to do maximum likelihood estimation of the parameters, for example, each step in our maximum likelihood estimation means you have to do this. So people have worked on sparse GPs, and they've reduced these complexities down from n cubed to nm squared and n squared to nm. And I think they're really concentrating on the complexity here, the computational complexity, n cubed to nm squared. But if you try to do this in practice on a modern machine, if you go out and buy the biggest machine that Dell will sell you, you're going to run out of memory way before you run out of CPU and run out of patience. A really big covariance matrix with 100,000 by 100,000 points in it isn't going to fit in the RAM on even a pretty big machine. But things that do fit in the RAM, things that will take 64 gigabytes of RAM, for example, you can invert them in less than a minute on a modern processor. So the memory is a big issue, and a lot of these things attack the computational complexity perhaps more than they attack the memory. And the point of my talk is they've done all this work on sparse GPs, lots of people have contributed, and it's just not good enough for big data. That's not enough of a reduction in computational complexity or memory storage in order to make it applicable to really large amounts of data. So what are we going to do about it? Well, in other parts of machine learning, they have parametric models, and they do maximum likelihood estimation in these models with lots of different fancy names that I don't entirely understand, but I'm reliably informed that it is maximum likelihood estimation via the Robbins-Monroe algorithm. And what they do is they take their parameter vector they're trying to optimize, and they've realized that the objective function, the log likelihood that they're trying to optimize, actually can be written as a sum of functions of the data points. So they can take a subset of the data points and just get an estimate of what the gradient is and move in the gradient direction, and then throw the data point away and get another data point, and then move their parameter vector again, and you can prove that this will converge to a local optimum in some way. And so you can do maximum likelihood estimation using practically no memory, because you only need to have a small number of data points in memory at any one time. And then just a couple of years ago, people started to realize actually we can kind of do this Bayesian models. We need a few more tricks, but what we want to do, instead of having a parameter vector and doing maximum likelihood estimation, we're going to have a probability distribution that's going to approximate the posterior. And the probability distribution is going to be parameterized by some vector, and we're going to optimize that vector such that the approximate posterior is close to the true posterior under some metric. And if you've got the right kind of probabilistic model, and it turns out then you get this necessary sum over data point structure, just like you did for the maximum likely parametric models, and it seems to work. And what I'm going to do here is show you how you're going to do that in a Gaussian process model. I'm going to need 2 tricks for doing that, which I'll introduce you to. And the reduction in complexity that I'm saying is so important. Now our computational complexity is m cubed per these per stochastic optimization step, whereas before it was originally n cubed and then nm squared. So we're now not dependent on n anymore to do the stochastic work. Okay, a recap of what I was saying the other day. Sparse Gaussian processes are usually viewed like this. We have a covariance matrix on the left. We're going to approximate this covariance matrix using some low-rank form. And then this form on the right here is easy to invert, it turns out. Or you can use the Woodbury identity to realize that you can compute solutions to the system much more cheaply than you can invert the full matrix. And one of the important things about sparse GPs, one of the things I think we should realize, rather than seeing this as a low-rank approximation to the covariance, we should be saying, well, how are we capturing information from the data? When we normally do Bayesian inference, we get some data and we have a model or a prior, and we compute the posterior by MCMC or exactly. And then once we have the posterior, we don't need the data anymore. And sometimes people define Gaussian processes as being non-parametric because you need the data for the posterior. But actually, you have a mean and covariance for the posterior, which is just some vector and covariance matrix, which are functions of the data. But you can just store those. And in a sparse GP, you can throw the data away. You just get a posterior. It can tell you what the mean and covariance of this posterior is. And it's Gaussian. And once I've got that, I know everything. So this posterior object is what we want, but we don't want to have to compute this full posterior. We want to compute some compacted form. So instead of computing the posterior for the latent function values f, I'm going to compute the posterior for a smaller set of latent function values, which I call u. So here's my picture from the other day. I've got some inputs to a GP, I've got some outputs, as the machine learning people would call them. So input space and function values, I call them x and y. There's some function that goes through them, which we call f of x. Some points on that function where we have data, the latent function values, I call that bold f. And I compute the posterior, which I'm representing by these vertical bars here. Now these bars are showing me the variance, but there's also covariance between them. But this is just a sketch of what's going on, and I'm saying in a sparse GP, we're going to introduce these additional points, u, and they're going to live on the function. They're really in the same space as f, but for historical reasons we've called them u. And my probabilistic notation now looks like this. I've got some likelihood p of y given f. I'm going to assume it's Gaussian for this talk. I've got the conditional p of f given u, and I've got p of u. And they come from the usual marginal or conditional properties of the Gaussian process. So it looks a little bit like this. Here's my original, what I call KNN, my covariance matrix. I've got these additional inputs to the process I call Z. I'm going to just stack those on the bottom of X. And I end up with these sort of chunks of the covariance matrix, and you rearrange these in some way, and you get that picture I showed you at the beginning with the low-rank approximation, which is made from these long, tall matrices. But that's where those matrices came from. They're really just additional inputs and outputs to the function. Okay, so here's my notation for what's going on here. I've got p of f, y given f, the Gaussian likelihood. I've got the conditional, p of f given u. And I've got what I'm now thinking of as the prior, p of u.
So you think your conditional should be inverse of KMM, right? With the
Yes, absolutely. That's well spotted. And I'm going to do exactly the same thing. I've got these other points on the function. Rather than this blue f, I've got this red u. And I'm going to compute this posterior for these points. And from that, I'm going to be able to make predictions for other parts of the function. So let's have a look at how we do that. We're just going to turn the handle on Bayes' rule. So we used to do p of y given f, p of f given x, and then integrate across and renormalize. And what we're going to do instead is do p of y given u, which is a smaller vector, p of u, or p of u given z, and then renormalize, and that gives me my new posterior. Simple.
But u is not a function. Is u the value or the input?
U is the value of the function, z is the input.
Right.
So
the u's are on the vertical, basically.
the u's are the values in the same space as f, and z is the inputs in the same space as x. I didn't choose the notation, I just kind of lumbered with it.
Well, but it's important, actually, one trick you can do is you can move u into a different space. So instead of observing the function value as something to store, you could observe the gradient of the function value and store that. Even though you never observe the function, you just might well say, it's good to know the gradient here. And
you could do any kind of multiple output.
It just has to be correlated with the thing you want to store.
Yeah, absolutely. So we're going to do this. So we're going to write down p of y given u, and then p of u, and it looks exactly the same as Gaussian process inference, right? And there's a really big sticking point, which is that actually p of y given u is hard to compute. So to get a p of y given u, I have to integrate across f, and that actually involves inverting k and n, so I haven't gained anything. So what I'm going to do, and what I'm going to argue most sparse approximations for GPs do, is approximate p of y given u. And what I'm quite interested in is, in these approximations, how are they different, what information are we throwing away, and when is the assumption kind of reasonable. So this is my favourite way of doing it. Here I've just got exactly Bayes' rule, but all conditioned on u. Well, usually you would see what I think was the posterior on the left-hand side, but I've got it on the bottom. And the marginal, which I've got on the left-hand side, you would see it on the bottom. But this is just Bayes' rule. And I'm just going to rearrange this a little bit, just by taking the logarithm. I haven't done anything fancy there at all. I've taken the log and just written this as a sum. And then I said, well, the left-hand side is not a function of f. And the right-hand side contains the likelihood and something that's almost a callback library divergence. So if I just take the expectation under p of f given u, then the left-hand side doesn't change at all because it's not a function of f. So I took the expectation under both sides of p of f given u. The right-hand side is a sum, the left-hand side is not a function of f. I end up with this thing. So I've got two terms which I'm going to call p tilde of y given u and this callback library divergence. And I'm going to argue that p tilde of y given u is a good proxy for p of y given u when u is good at explaining f. And that's exactly what this callback library divergence is telling me. It says that when the distribution for f given u and the distribution for f given y in u are the same, as in u contains all of the information that I wanted to capture from y, then this is a good approximation. Okay, so what does this p tilde look like? So I'm going to throw that term away, that callback library divergence. I'm going to use this p tilde of y given u as my approximation, and it looks like this. So the other day I talked a lot about this penalty term here, which does very sensible things to where you put the inputs to the process. But today I want to concentrate on another facet of this, which I think is much more important for what I want to talk about, which is that this now factorizes in the data. So I can write this as a product of sum of terms in yi. So this red term here, you notice, isn't a function of u, it's not a function of f, it's not a function of y, it's a penalty term for throwing away that callback library divergence, if you like. And actually you can show that this will be small when that callback library divergence is small, quite straightforwardly. And the black term here factorizes in n, and that was the property that I wanted to exploit in order to get this Robbins-Monroe-like algorithm. I said that to do this, to do the original Robbins-Monroe for maximum likelihood, I had to have a likelihood that could be written as a product of data terms, or a log likelihood that's written as a sum of data terms, and then I can get an approximation for it. Now I've got something that's product or a log sum of things in the data points. That was what I wanted. Peter?
Just to not make sure, but at least admit the possibility, I'm still understanding. This is going to work well if you've got smooth correlation functions, right? And not so well if you've got very spiky.
Yes.
Right, got
it will work well as long as you explained F well.
Equal, yeah, that's right.
Yeah, so that's exactly one case. So if you've got a lot of...
The K and N term there is exactly the posterior variance, trying to predict the training data given the U's.
Yeah.
So if there's good communication between your U's and your F's, then this penalty term just disappears.
Yeah, and your problem becomes... And also the callback liability evidence, you can show that goes small, so it's a good estimation. The simplest case is if you imagine you have many observations at the same point, then you could obviously represent them by one observation at that point, and it would be perfect. So if you spread the observations around a little bit and you put some points scattered amongst them, it's going to work well.
Another interesting degenerate example is if you've got a linear covariance function, so if you just build a degenerate covariance, the number of U's you obviously need is the same of the rank of that degenerate covariance.
Yeah.
So, and that's clearly true as well. But you normally don't do it in this complicated way, you just express it properly in the low rank form.
Yeah.
Excuse me?
Okay. Yeah.
How do you choose your subset from the data? How do you choose your subset from data? You take Z.
I see. So Z isn't necessarily a subset of X. It might be, but in what I would call the full sparse method, where I'm going to marginalize out U, that I talked about the other day, you can then pick some Z, either from the data or near the data, and then optimize them along with the covariance function parameters. And that turns out to work very well.
The problem is if your data is unbalanced. You have large data, but it's unbalanced in terms of classes. For example, you have lots of positive classes and very few negative classes. Then if you will take this subset, it might be from one class only.
Yeah, that's an interesting idea. Okay, so we've studied that somewhat. So you're talking about if we have a classification problem, and this is slightly back of the envelope. We've sort of noodled around with this in the lab and never published anything. But what happens if you're going to need to do something to approximate the system now, because it's non-Gaussian, we can't really do this. I'm not really talking about that. But if you did the most popular machine learning approximation, which would give you a Gaussian approximation to the likelihood, you would find that where the problem was misclassified, let me get this the right way around, where the problem was misclassified, you had a high likelihood variance. And where the problem was well classified, you had a small effective pseudo likelihood variance. So where the problem was well classified, you could say, okay, I know exactly what the function value is doing here, but where it's poorly classified by the system, it's not. And this little sigma squared here is the noise variance. So in the case where each likelihood term had a different noise variance, that would have a little index on it, and you would get exactly a penalty for not classifying things very well, and you would move towards the informative parts, with the informative data as well as just amongst the space. So that sort of penalty term does that as well. But I'm waving my hands a little bit here. But that's we've played with that, and it seems to do something like that. Shall I move on? Right. So what people then do, although they may not have approached the problem like this, to say I've got this p tilde of y given u, and I'm just going to do Bayesian inference. I'm just going to turn the handle on the Bayes rule here, get an approximate posterior for u, and then we can use it to get the marginal likelihood, which appears on the bottom, to optimize my covariance function parameters. I can use it to make predictions for new points that I want to know about. P of u given y, or p tilde of u given y and z is what I need. But that's where the nm squared complexity comes in. I don't really want to do this. So if you want to see exactly this method, you can go and read Mikhail Stitsi's paper from 2009. But I'm saying this doesn't scale to big data yet. But what I can tell you is that that posterior is a Gaussian in U. So you can do the linear algebra and it turns out to be some nasty thing, but it is a Gaussian with some mean and some covariance matrix, which are some function of the covariance matrices that we've been through in the rest of this talk. So what I could do is say, well, I'm not going to do exact Bayesian inference, I'm going to do approximate inference. But in this case, it's not very approximate, because I'm going to say, I'm going to parameterize the family of Gaussian distributions with mean and covariance matrix, and I'm going to optimize that to get it close to the posterior. And I know that the posterior is in the family, so I know that I can get an exact representation of the posterior. And actually I can prove also the problem is convex. There was only one solution. That should be pretty obvious from the way we did the integral up there. So I'm going to have a guess at the mean, have a guess at the covariance matrix, and then I'm going to optimize those until they're close to the posterior, using what machine learning people call variational Bayes, and I should get there. And whilst I'm doing that, I'm also going to adjust the height parameters, because I've got a lower bound on the marginal likelihood, which I'm going to use as an objective function, and I'm going to adjust the covariance matrix parameters as well whilst I do that. And every adjustment of the approximate posterior, which I know will converge to the posterior, and the adjusting of the covariance matrix parameters costs very little indeed. In fact, it costs m cubed, where m is the number of these extra points that I've put in. So I'm quite happy to have m at 1,000 on my little laptop. No problem. Okay, so this is what machine learning people have been doing in all kinds of other models, not just Gaussian processes. They have this thing called variational Bayes, and it's exactly how do you approximate some complicated posterior with some simpler one. And they make some assumption about the posterior usually, and this is usually difficult to bring up in a room with statisticians in it, because they say that never converges to the posterior. And you say, I know, but it still works pretty well. But in this case, the posterior is in the family that I've got, so I know that I will converge to the posterior. And I have procedures for updating these things, and they're kind of complicated. How am I doing for time? I've got another 20 minutes?
Good question. Let me look it up. You're 5 minutes over on the original schedule, but in the updated schedule,
15-ish? 20-ish?
Yeah, well, the slower you are, the shorter coffee break we'll have. Yeah.
Oh, well.
So I shan't go whether people glare at you or not.
I'll just judge. I'll fit some kind of log Gaussian Cox process to the number of people who are sleeping, and then try to estimate the rate, and then we can work out when we're going to go for coffee.
What size? Oh, yeah, I don't know. I don't even know when you started.
Okay, so the other people were doing machine learning, and they were doing stochastic variational inference. They said we're going to do this approximation procedure where I move this approximate posterior so that it's close to the true posterior. And they said I can do this using the Roberts-Monroe algorithm if my graphical model looks like this one here on the left. And they said I've got some data points yi and maybe some latent variables zi, one associated with each observation. I've got some global variables, which are called g. And you immediately look at this and you say, well, I can't do this in the Gaussian process at all, because my Gaussian process looks like this. I've got these latent function values f, and I've got these observations y, but all of the f are correlated. I've got this loop around the plate here which says that they're not independent. Okay.
10 minutes, or is that too late?
I was going to leave 10, 12-ish.
Yeah, that's it. Uncertainty, that's it.
Yeah, a little bit of uncertainty. So, the hero in the story is p tilde. So once you rewrite this model as p of u, p tilde of y given u, the model looks like this. And this is sufficiently close to the model on the left a second ago that we can now steal their inference procedure for doing stochastic variational inference. So I've got this distribution I call q of u, and I do this machine learning trick, which looks kind of horrible, but really isn't that bad, I promise. And much the same way as I sort of got rid of the variables f earlier in some approximate way, I'm going to do the same thing here. But I'm telling you that at the optimum of this thing with respect to the parameters of q of u, I recover the exact Bayesian methodology. As long as you believe in p tilde of y given u. P tilde of y given u has now become L1 for notation reasons. Okay, so this becomes a sum of terms is the important thing. I can write this as a sum of terms which cover the each data point, and now I've got some things to optimize. I've got the parameters of q of u, and I've got the parameters of the covariance matrix, and to get the gradient of this, or a stochastic estimate of the gradient of this, I can just take a random batch of data and then move in that direction. Okay, so that's what I'm saying here, and so far all we've done with Z is just pick them from the data initially. What I came as clustering. I know that there is some work on how we can do that. Do something sensible with Z in this setting, but I don't think it's come to anything as yet. So this is what I said. We're going to optimize this objective function which moves q of u close to the posterior and improves the covariance matrix estimate as well. And I've got this extra trick that I want to talk to you about in my remaining 8.5 minutes, which is called to take natural gradient steps to the parameters of q of u. So before I talk about natural gradient steps, does anybody have any questions?
Just guarantee that you have that your true distribution is the same family as your approximate distribution. Is that conditional on the form of your likelihood of y given f?
It's conditional on
Of p of y given f, just as long as you're doing regression, then everything's well behaved. If you suddenly start calculating...
yes, p of y given f is Gaussian in this case. So I thought about extending this to when p of y given f is not Gaussian, and then no, is the answer. But there's lots of... I can then relate that to other machine learning methodologies which have various proofs around them that are interesting. But
that's a sort of second greedy. So does the random nature of this stochastic gradient descent methods actually make you better at avoiding local minima? You could get away with some sort of like pseudo annealing approach. If your argument is a bit mad and does do strange things.
Yeah.
So they claim in the field of stochastic gradient descent. We wouldn't ever possibly claim such things.
Okay, no, that's a really interesting point. We can come back to that.
It comes up a lot. Joshua Benjo will talk about a lot of this. Because it's a stochastic gradient, you're actually... So it's like working with a noisy gradient, which is going to move you around. Just because in the deterministic gradient you're going to go to the solution, with making that gradient noisy, you might go to a better solution. I don't know about the proofs, it's not our area of expertise, but they do say that in that field, and the same thing presumably apply there.
But, yeah. Rob.
Can you set Z outside of this?
I do set Z outside of the loop at the moment.
You do?
I just take all of the data X and I tried a few strategies, like just picking them randomly from X. I've tried doing k-means clustering on X, which actually works pretty well. That's what I used in the end for the examples that I'll whiz over. And actually Nick Golding, I think has left, suggested some kind of cool coverage thing which we can do well.
I mean, I wonder if there's any design theory that you could bring to bear on that.
In some sense there is, because you can see what it should be optimally in the Gaussian case, because that penalty term tells
Exactly,
you...
well, that's the point. You know what the error is mathematically.
Yeah,
but it depends on the covariance function.
It actually then
depends,
and it depends where you want to predict, because actually you now have this ability, which is really interesting, that you could decide to actually put these inducing points where you want to predict rather than where you want to learn. So maybe you want them different at test time than at training time, depending on whenever you want.
No, that's an important point, because when we make predictions with this thing, we recover what I think of as the non-parametric part of the model. So when you make a prediction, you do exactly what you do for a Gaussian process. You do integral p of what I call f star given u, p tilde of u given the data, and then you recover what machine learning people think of as a new basis function for every point that you make a prediction at. So it still has this non-parametric essence to it, what I think is the important part of the non-parametric essence.
There's some interesting, actually it's true, there's some interesting designs you might consider where you put out points near where you want to predict to ensure you get the short length scale behaviour correct, and then some distant from where you want to predict at training time to get the longer scale correlations.
Yeah, that's
so that you're
interesting point.
focusing the entire model on...
But on the other hand, if you don't have well-spaced Z in the data, you won't get a good estimate of the covariance. You have a bias on the covariance estimation.
Well, there is always a tension between designing for estimation and designing for prediction, that's for sure.
Yeah, that's really interesting because there are two schools of thought in machine learning for how you should do approximate inference and this kind of thing. And one of them turns out to be to include independent predictions for all of the training points, as if you were trying to predict for them in your objective. EP turns out to look an awful lot like that. And another school of thought is that you should just optimize it for inference. So I don't think that's not been very well explored, but that's an awful lot what it looks like to me. Okay. Simo.
So if you look at if you want to optimize the test point predictions, you cannot do just likelihood-based inference because the likelihood just tells something about the training set. So you need to put some other utility function or loss function that you optimize, something like that. That's related to design theory.
Yeah, because you don't have the data point yet, so you can't tell what the likelihood is. Yeah, that's true.
But instead you can take expectations over some suitable distributional model.
From the training data. Yeah.
Well, for example, I mean, you can think of integrated mean square error as a kind of an average over a uniform distribution of prediction points. And sometimes you don't want that because there are particular areas that are more interest than others.
Okay. I've got a few minutes to talk to you about the natural gradient, which is my favourite part of what's going on here, and I think really the crux of why this works. If you don't know about the natural gradient, you can't do this. It just doesn't work. And so this brief interlude, I really need to know who travelled the furthest to get here. Anybody come from the US? No? So there were some people from Sweden?
From
it must be. From Makaroa.
Too quiet to admit.
Anybody want to try to beat Uganda for distance?
It was Brazil, yeah. Someone from Brazil. They don't. There we go. Brazil.
I think maybe you win. Okay.
They're nicely distributed across the room.
So I'm going to use Rio de Janeiro as my example. So which direction is Rio de Janeiro from here? Is it over there? That way as well. Anybody else? Okay, so suppose I'm trying to get to Rio de Janeiro on foot, and I've had a little word with the Lord, and He's allowed me to walk on water for the week, and I'm going to ask you which way it is, and Rob very confidently says that it's over here, and I'm going to be like, right, well, okay, I want to take this angle in latitude and longitude. So I look at a map, I've got Sheffield on the map, and I'm like, okay, well, I want to move like 12 degrees south and 28 degrees west, for example. That probably doesn't get me anywhere close to Brazil. This direction here, and I walk for 2 hours in that direction. And then I ask the next group of people that I'm talking to, because they've all followed me, and I say, which direction is Rio de Janeiro? And they say, it's this way. And I walk in a straight line. Do I end up in Rio de Janeiro? I think I do, eventually, but have I taken the shortest path? No. So what's happened is, if you're interested in maps, and you've looked at maps of the world, you might understand the Mercator projection, or the Peterson projection, and whenever you get the globe and you squash it onto a piece of paper, you must distort it somehow. So you must have introduced some kind of curvature. And when I say what direction is this, we're kind of fitting a plane to what we're standing on, and over there, the plane is way off the surface of the Earth, so the approximation doesn't work very well anymore. This seems like an enormous tangent to what I've been doing, but it's really important because I'm optimizing parameters of Q of U. And Q of U actually gives me a geometry not totally unlike a sphere. So Q of U, let's suppose you were naively trying to implement this, you might implement it with a mean and a covariance. A mean vector and a covariance matrix. And then you would take a derivative in the mean vector and a derivative in the covariance matrix and take a little step. And then somebody would come along and say, oh, I've got a different implementation. I've actually got the mean times the precision matrix and minus a half times the precision matrix. And that gives me valid Gaussian distributions as well. And he says, well, I've taken a step in the gradient direction as well, and we're in different places. because the parameters are different. Much like taking steps on the Peterson projection or the Mercator projection will end up give you different places if you move in a straight line. So what we want to do is move in a straight line, but according to the geometry of what we've got. So on the Earth, or on any sphere, the straight line, if we start thinking about straight lines as being the shortest distance, they sound to be great circles, like the largest circle that you can fit around the surface of the Earth. And if you follow one of those, you'll get back to the original point. I think that's the definition. And if you fit one of those between 2 points, that's the shortest path along the surface. So that's what we want to do, but with probability distributions. So this becomes a little bit ugly. But some very clever mathematicians have done a lot of work for us, and they say, well, all you need to do is consider the curvature of your problem. So if you know the curvature of the Earth, then just multiply the inverse curvature matrix by the gradient vector, and that will move you along the great circle, at least locally. So let me show you some examples of that. I'm running out of time, but here is a little bit of code that produces this plot. So I've kind of got a sphere here with an objective function on it that I'm trying to maximize. The objective function is shaded, and what I've done is I've taken little steps in the gradient direction in the parameters latitude, longitude, or azimuth and rotation around the thing. And that's the pink line. So I've evaluated the gradient, I've taken a little step, evaluated the gradient, taken a little step, and I end up moving on that pink line. If I do exactly the same thing, but I multiply by the inverse curvature, which is really straightforward to calculate for a sphere for the gradient step, then I end up moving along that pale blue line. So you can see the pale blue line is a whole world shorter than the pink line, and just imagine this in hundreds of dimensions, because you've got a covariance matrix or a mean vector that you're trying to optimize, and this becomes really, really significant. So what's the curvature of the distributions I'm trying to optimize? Turns out to be the Fisher information, which I call G. Other more enlightened people might call it F for Fisher. So we take the inverse of G and multiply the gradient, and they call that the natural gradient, and that's the direction that we want to be moving in, because it moves us along these geodesics of the probability distribution family. And for exponential families, which includes Gaussian and almost anything else that you probably want to parameterize, there's this really cool trick that says I can get away without computing that matrix inverse. It's fairly straightforward to calculate, but it just says that the derivative, the natural gradient, which I'm calling G tilde here, I like tildes, is the inverse Fisher times the gradient, but it happens to be the derivative in a different parameterization. So the exact...
on a log scale with these probabilities now, because because that looks a bit like Fisher scoring on Newton-Raphson.
Looks a bit like Fisher's?
Fisher scoring on the log value.
Well, okay, I'm going to have to ask you about that afterwards.
Yeah, I think it's the same thing. It's just different language with the same idea. Yeah.
Okay, sounds good. Yeah, so that is
Fisher information matrix.
L is the objective is the objective function I'm trying to maximize.
Which in the context in which the phrase Fisher scoring is used is always the log value.
There's a bound on the log line.
Yeah.
Got it. Nice.
So this is the direction I want to move. So this is fairly straightforward to prove.
Fisher scoring.
Oh dear, I've overrun.
The tradition in Britain with fire alarms is to sit there for 5 minutes seeing if it's a real alarm or not.
But if this is about, you're about to think that it's a real alarm, then the alarm goes off. Now that is just gonna, if you have to be out of the building within a certain amount of time, that seems the stupidest thing to have set up, that everyone sits there every time the fire alarm goes.
Yeah, we should do some kind of risk analysis. You know, they test the fire alarms every week, but it makes people kind of ignore the fire alarms.
makes everyone
So
go,
to make the fire alarm much less effective?
Unbeknownst to you, that's maybe what you're doing it for. They didn't come out.
Okay, so now what we're going to do is take our objective, which I've called L3, we're going to try to maximize it with respect to the parameters of Q. U, which are either theta or eta, depending on whether we're using, for Gaussian, they could be the mean and the covariance, or exactly what I said earlier, the precision times the mean and minus a half times the precision. So one of them is the canonical parameter and the expectation parameter, example. And that's cool because we can get away without inversing g of theta. That's a really important point. And there's some work going on at the moment about, because we're going to take stochastic versions of this, we're saying that people are looking at the sort of variance of the estimator for this natural gradient and how we might compute it, and whether that's actually a good thing to do. But this is the general idea. So what happens is you compute this natural gradient, and the updates become like this. And there's a nice result here, which you can show that if you take all of the data set and compute the natural gradient, then it converges immediately to the true posterior in one move of length 1. Which is kind of a nice result. And that also gives you a good idea of how long your step should be. If you had no bias or variance in your estimate of the gradient, then you should move length 1. Okay, that's enough technical nonsense.
Is it also true that would be the E step in an EM algorithm?
Yes, it would.
To do that, that would be precisely the E step of the EM algorithm.
So this is, if you run on similar code, we get plots that are like this. And this, on the bottom here, we're looking at the stochastic estimate of the lower bound on the marginal likelihood, the thing we're trying to maximize with respect to the covariance function parameters. And the top here, we have the values of the covariance function parameters. And you can see that they sort of converge-ish, and they wiggle around a bit before they converge. There are a few tricks we have to do here. So we've actually optimized Q of U with the covariance function fixed for an iteration. That seems to help an awful lot, otherwise it might just explode on you. But generally speaking, it sort of seems to work. And we can do things like
interleaving lots of little E and M's, isn't it? And the first thing you said is like trying to do a big E step before you start interleaving these E and M's.
Yes, exactly. That's exactly what we're doing. Okay, so the government kindly provided us with the cost of housing in the UK, which I thought would make a nice plot. There are 75,000 apartments that were sold during this period that they released the data for. So I cleaned the data and ran it against a latitude-longitude database, which I think might have come from Peter's website actually. And we get a map like this. This is the normalized logarithm of the cost of an apartment in the UK. And now you can see why none of us live in London. But the important thing is I think I have 1,000 inducing input variables here scattered across the whole country, and I can get short-range correlations captured in this thing that I couldn't have done with my 75,000 data points.
And also Cardiff, where we don't live.
Yes. It's nice to be at the mean somewhere. Of course, I can get the predictive variance. So this is the marginal of the predictive variance. It's high where nobody lives because there's no data there. Like in the sea, it's high. In national parks in Wales, it's high. And in other places where nobody wants to live, it's high. That's exactly what you would expect it to do. One more example before I finish up. I also applied this some airline data. We looked at the how long your flight's going to be delayed. So we get some parameters about your flight, like what day it is, what time you're flying, what airport you're flying from, and so on. We're trying to say, well, the output variable is how long is your delay. And there are 700,000 training points here. And if you just take chunks of the data and fit GPs to that, you might say, well, let's try that before we do any of this fancy stuff. How well does it do? But actually, as soon as we start taking 800, 1,000, or 1,200 points, we're still not getting even close to the root mean squared error we can get using our method. And because we have to optimize the covariance function parameters, actually we're in sort of comparable time to using about 1,000 data points here. Another question is, how many Z should I use? How many inducing points should I use? And does it work well? Do I need to just keep adding them? Will it ever stop? So here's the same plot as before, the root mean squared error against iteration, but with increasing numbers of M. So thankfully, the root mean squared error goes down as we continue to train. But as we increase M up to 1,000, we seem to converge. It doesn't seem to get much better after 1,000 or so points on here. If you read our paper, we have some comments about when you should go flying, basically. The code is mostly available in GitHub. This is obviously a little bit preliminary, so they're not shouting about it for general release. But if you want to have a noodle around, send me an email, and we can share. And there's a citation there for you as well. Good one.
Questions for James? Well, and if you want to start kind of setting up.
So your optimization curve had a bit of an oscillation there, and I was wondering, so you've shown formally what the noise was. You said step of 1 would be kind of optimal if you don't count the variance.
If I don't account for the...
I forget the details, sorry, but you said the optimal step of 1, under certain assumptions, you'll get there in 1.
So you're saying, I think he's referring to when you